Today, let us talk about Laplace equation. Laplace equation. Now, in the first few lectures, we have talked about first order equation, right? So, ut plus ux equals to that sort of equation, yes? Transport equation, Divergence equation, that sort of thing. But now we are transitioning into the second order equation. Why Laplace equation? Let us understand this thing first. Why Laplace equation? See, the point is, this is the most basic second order equation of elliptic type. If you remember from earlier PDE courses, what happens is most of the, if given a general linear PDE, okay, PDE, okay, of the form, so second order, how does it look like? If you remember, it will look like this: a u x x plus b. I am not writing all of this, but a depends on x y, so I am talking about two dimensions, and b u of x y plus c u of y y plus d u of x plus e u of y plus f u plus, let's say, g equals to 0. Yeah, that is a expression. So all of this here, all of these coefficients a, b, c, these are all azimuth. I'm not writing all that. So okay, so let's just do that. All of these coefficients g, these are all continuous. Let's say these are smooth coefficients in R2 here. So that depends on x and y, where AB and all of this is in C infinity R2, right? Now the point is this: if you remember your canonical form, so the canonical form of this particular general equation, canonical form, okay, I hope you understand. So what I meant by this is, see, any second order linear PDE can be written in this form here. Canonical form, let's say that is your one, let's say that is your star, let's just call it star. So canonical form, what it does is, actually, if you in a more suitable coordinate system, okay, so what it does is, under a suitable coordinate system, right? Under the suitable coordinate system, star gets, okay, so under the suitable coordinate system, star gets reduced to either of the following. So what is it? It is either wxx plus wyy plus some lower order terms, containing wx, wy, and wx and y, that is equals to 0, or wx minus wyy plus lower order terms containing wx, wy, wxy equals to 0. Yeah, or you can have this form, number 3, wxx minus wyy plus some lower order term containing wx, wy, wx and y. Okay, what this canonical form does is, it does not change the nature of the equation. If you remember, if you look at the discriminant of this equation, yeah, and depending on the sign of the discriminant, if it is negative, it is elliptic; if it is positive, it's a hyperbolic problem, and if it is 0, it's a parabolic problem. Okay, depending on that nature, if you do a suitable coordinate change, okay, coordinate change, then what happens is, you can reduce this to something like this. Okay, this particular equation is an example of an elliptic equation, right? Okay, this equation is an example of a heat equation or a parabolic equation, and this equation is an example of a hyperbolic equation. Let us understand what I mean by this. So let me again recall what I am doing. See, essentially we have a linear second order PD which looks like this. Yes, all the coefficients are smooth. This is what we are assuming. What canonical form does is, see, this is in some coordinate system x and y, right? You can change the coordinate system to uv. So here you can change xy to uv, but I mean it does not matter. These are all variables, right? You can write xy, you can write uv. So essentially, under the new coordinate system, you can actually change a star, okay, to one of the following this thing expression. So let's say if this star is a elliptic equation to begin with, there is a change of coordinate which will actually transform this to this. Yeah, this is much easier to solve. Yeah, this expression. So essentially, we are only interested in the higher order terms. Lower order terms, I mean, those we can handle. Higher order terms. So it will look like wx6 plus wyy. Okay, that's the elliptic problem. Again, if the original problem is a parabolic problem, under a change of variable, it will look much simpler, which will look like wx6 minus wyy plus lower order term. So essentially, this is also a lower order term, but I'm just writing it in this way just to make it look special. Okay, so familiar. It's like a heat equation. So that's parabolic form. So you understand? Otherwise, I mean, you can just take this wx over here also. It's not a problem. And wxx minus wyy plus L of this is equals to 0. That's a hyperbolic form. So essentially, this is like a wave equation form. Two second order terms plus lower order term like this. Okay. So where, let me put it like this, where L of are the lower order terms. Okay. Now, so let me make a small remark. I am assuming here that since this is an advanced PD course, I am assuming that you guys know all of this. Okay, if you do not know, please choose a suitable textbook. Okay, whatever you want. You see, most textbook contains this thing. Yes, please choose a suitable textbook. For example, Mint and Devnath. To review it. Okay. See, this the thing which I said. If you guys are familiar with this thing, there is absolutely no issues there. If you are not, then obviously you can just choose any textbook you want. I mean, this is just an example. Okay, Mint and Devnath, partial differential equation. This book, you can just look at that book and just review this. Whatever I said, it's not very difficult thing to do. Okay. Now, what is the point of all of this? The point of all of this is see, if we want to study most linear equations, you do not need to know, you understand, you do not need to know how to solve a general equation like this, okay? All you need to know is how to solve these three prototype equations. If you know how to work with these three prototypes, you are done, right? Because ultimately, any linear equation can be reduced to something like the second order, okay? Any linear second order equation can be reduced to one of these three forms, right? So if we can just study these three forms, these are the fundamental forms. If we can just study these three forms, so basically we call this an operator. L of w is wx plus wy. Okay, how these operators behave, yeah, then we are done. So then we can actually work out our problems. Okay, so let us start by first of all with the example. So we define L of u. So this is what I mean by an operator. Okay, define L of u to be u xx plus u yy. Okay, before I move on doing anything, I just want you to take 15 seconds, 10-15 seconds and think about if what is L. So L is supposed to, as you can understand, it's kind of a function, right? It is taking something and putting it into something, right? It is taking a function and giving back another function which looks like this. So can you tell me where is L defined from? Just take 10-15 minutes, seconds, and just think about it. Right. So let me just tell you where it is. See, L is an operator. What do I mean by operator here? So L is a linear operator. Okay. What do I mean by linear operator? What I meant by this is essentially see, it is taking values from some vector space U. See, if I'm taking a U, UXX and UYY has to be satisfied, right? So U has to be at least twice differentiable. So it is C2 of whatever the domain it is. Yeah, I don't care, some domain. Let's say omega. I'm starting out with an omega which is subset of R2. So L is from C2 R2. You are choosing an element of twice differentiable element, okay, and it is giving back UXX plus UYY. If U is twice differentiable, UXX is continuous and UYY is continuous. The sum of two continuous functions is continuous. So it is giving you back something like this, okay. So L from is a linear or second order operator, okay, operator. This is what I mean by operator. So you see, this is also a function, but in a special way. What is so special about it? That it is not taking elements from any ordinary set, but a vector space, okay, of functions. Okay, it is taking elements from a vector space of functions. Right. Now, let us look at where all of this comes from. So let us look at some physical motivation. Yeah. So before I do this, let us put some name to this particular operator. So Laplace equation. Okay. Laplace equation. If you are looking at an equation which looks like this, Laplacian of u, that is given by divergence of gradient u. Okay, if you remember, gradient u is, let's just start with two dimensions. Okay, don't worry about n is exactly the same. Okay, let's just start with two dimensions. So in two dimension, gradient of u is ux and uy, right? So divergence of gradient of u, that is uxx plus uyy. Okay. Okay, so this is uxx plus uyy. Okay, that's your Laplacian. Now there is something. This equation, this is not an equation anymore. I mean, this is just an operator. Now, this, if it is 0 equals to 0, then it's called a Laplace equation. Now, we also talk about a similar equation which is called the Poisson equation. Okay, so the name is Poisson equation. This is, most probably I'm not 100% sure, but Poisson is just it's like a fish in French. Okay, so the equation looks like this: minus Laplacian of u. Okay, minus, there is nothing special about minus. You can write it, you may not write it. This is just a convention. Minus Laplacian of u equals to f. Okay, that is called a Poisson equation. Right. Okay. Here we will assume x is in from omega, which is subset of Rn, right? So what I meant by x is an n tuple, x1, x2, xn. Clear? Okay, I have used a something. Okay, so let me change this thing. So maybe let me do it for from now on. I will do it for Rn itself. Okay, okay. Actually, this is the problem. You see, I should write it like this. Let me change this part. Huh? Let me change this part. So in two dimension, it will look like this: x1, x1, okay, x2, x2. So essentially, your x1, x2, okay. So I'm just writing a tuple in R2 as x1, x2. Huh? You can write it as xy also, but in that case, you can't. I just want to, reserve x for a element in Rn. Okay. So x is x1, x2. So essentially, when I'm saying it is an element of Rn, what I meant is, so let me put it here to be Rn. So this is u xn xn. See, n equals to 2 is just this. Huh? Here I just want to write x is in omega subset of Rn means x. So essentially, x is x1, x2, xn. Okay. You do not have to worry about xn. the n components, just two component, whatever it does, n component, same sort of thing. Okay. Okay. Now, Poisson equation is minus Laplacian of u equals to f. This f will be given to you. U from omega bar to r is the unknown function which you need to find. Unknown function. Okay. And f is any given function on the open subset of Rn. Clear? So just think about it. What I'm saying, what I said is, you are looking at a u which is from omega bar. Omega bar is an open set, right? As I told you, if I am not specifying what exactly omega is, all the time in this course, just assume omega to be an open set in Rn. So omega bar is a closed set, the closure of omega to R, that is an unknown function, and f is any given function on an open subset of Rn. Clear? Okay. Now the question is, you just have to find what u is. That's the question. Okay. So I will start with a small definition here. Definition. So let's say a C2 function, u is called a harmonic function if it satisfies the Laplace equation, right? So if you are looking at a u such that Laplacian of u equals to 0, then that sort of function is called a harmonic function. Okay. Now example. Take 5 seconds. Just think about an example of a harmonic function. Okay, let me tell you what is a very easy example. Let's say let's say omega to be r n, okay, and u of x1 xn to be identically equals to a constant. Okay, constant. Okay. Now, if that is the case, what do you think Laplacian of u should be? Any derivative of this is 0, so Laplacian u equals to 0. So that's a trivial harmonic function, right? And of course, one special thing about harmonic functions are, okay, 0 is always included. So 0, so ux equals to, since constants always hold 0, therefore ux equals to 0 is always harmonic. Always harmonic. And this is harmonic in any domain, right? I mean, it does not matter. Whenever you can take any omega you want, omega is any open set, and u of x is always going to be a harmonic function. Okay, so that's one example. Can you think of another example? So let us assume that omega is in open set, and u of x1, maybe, I don't know, maybe x1, x2, xn, let's just call it. I'm writing it for xn, you can just think of 2 dimension also, no issues. So let's say that is xi, whatever I is, I can be 1, 2, whatever, n. Now, if that is the case, let's look at what Laplacian of u is. Laplacian of u, in this case, is u x1 plus u of xn. Now, I don't have to calculate this thing. You guys can understand that this is going to be 0. Okay. So, any coordinate function, this sort of function is called a coordinate function, right? Any coordinate function is harmonic. Okay. Let's take another non-trivial function here. So, in 2 dimension, let's just think 2 dimension. x1, x2 to be x1 square minus x2 square. Let's see if this is harmonic or not. It may be, it may not be. Let's just look at it. Laplacian of u is uxx x1 minus uy1 plus uy1. Okay. Now ux1 as you can see, the first derivative is 2x1, second derivative is x2. So that is 2 plus u y1, sorry, it's not y1 y1, it is x2 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 x2, okay, and plus 2 x2 x2 is minus 2, okay, that will give you 0. So Laplacian of u is 0. So hence this is an example. Therefore ux1 x2 given by x1 square minus x2 square is also harmonic. So there are, I mean, there will be other examples also, but these are more or less the basic examples of harmonic function. Okay, before we move on, let us look at what is so special about harmonic function. So uh, first of all, properties. Properties, okay. We define h, yeah, h to be the set of all C2 omega bar functions such that Laplacian of u equals to 0. Okay, so this is the set of harmonic functions. Set of harmonic functions. Harmonic functions. Okay, H is a set of all C2 omega bar functions such that Laplacian u equals to 0. So that is the set of harmonic function. Now I want to see what are some special properties of this set. See, let us say that let F and G are in H. Okay, let's see what happens. Define and define and define A plus G, yeah, acting at X to be F of X plus G of X. Okay, if I define it like this, clearly see, if this is the case, then Laplacian of F plus G, yeah, this is going to be Laplacian of F plus Laplacian of G. Okay, how is this true? Because of linearity. Yeah, if you are not convinced about this thing, I am not proving all of this. Yeah, it is going to be time consuming. I mean, it is not, it is just 2 lines, but please check this part. Yeah, it's not very difficult. Moreover, you see, for a C in R, for any C in R, if you define C times F acting at X to be C times F of X, and F is in H, okay, you start with a F in H and C in R, and you define CF like this, then Laplacian of CF, let's see what happens. It is definitely C times Laplacian of F. Huh? This also you can check. Please check this part. Huh? Check this. Check. Check. Okay. Now think about this. If you consider this property that if given two functions f and g, the sum is linear and the constant times f is also in h, right? So this definitely belongs to h. It means that CF belongs to h. Okay. What does that say? It says therefore H is a vector space. Vector space. Okay, H is a vector space. So this is very special about it. This is all of this is happening because the operator is a linear operator. Okay, since delta, so this is called a delta. This symbol is called delta. Is a linear operator. Linear operator. Clear? Okay. Now, what we are going to do is we are going to look at some physical interpretations. How, where do we use this sort of operator? Okay. See, this is the most widely used operator in all of partial differential equation, and probably one of the most important objects in all of mathematics, Laplacian. Okay. So it is very important that we know, understand, and appreciate what, how beautiful this operator is. So let's look at some physical interpretation. Physical interpretation. Okay. So first of all, let us assume that U is the density of some chemical concentration in equilibrium. Okay. Let us assume U is some function. Huh? So this represents the density of some chemical composition. Okay, I mean, some substance is given. You are looking at the chemical composition of that thing. Okay, in equilibrium. Equilibrium. Yeah. Okay. Equilibrium is when it is stable. Okay. Now, let us say that the chemical is contained in some, region which we will call as omega. So the region we are where the chemical is contained. Clear? So that's your omega. Omega is our domain. Okay. So let us see what happens. See, let's say that's your omega. Huh? That's your omega. Yeah. Now let us assume that V is some V. Yeah. So let V be a smooth. Okay. V be a smooth region contained in omega, right? So that's your V, let's say. Yes? Any smooth region which is contained in omega. Now, if that is the case, there seems to be some problem with the software. Okay, let's just take another page. Okay, so if that is the case, then so basically what I'm saying is if V is a smooth so contained in U smooth is smooth. Okay, so what am I doing? That's your U. Okay, and this is where the chemical is. So the chemical is, and U is the density of the chemical, and that chemical is in equilibrium, and you are just looking at another small sub-region, okay, which is V. Sorry, this is not U. I'm calling it an omega. V is contained in omega. That's an omega, right? Okay. Now, you see, since the chemical, yeah, the concentration that is in equilibrium, the chemical is in equilibrium. Okay. So therefore, the net flux, So net flux means whatever is going in or coming out. Okay, of you through the boundary of V, del V, is zero, right? This is quite easy. And if that is true, what does that say? Del V F dot gamma ds is zero, right? So basically, there is no flow of the flux density is not changing, yeah, in the unit direction. So let's say gamma is this. Gamma is the unit outward direction. Okay, so where F is the flux density, and gamma is the unit, okay, outward direction. So what I meant by this is, uh, see the whole liquid, yeah, or whatever the chemical is, it's in equilibrium, right? So if you look at a small region, wherever on the omega, small smooth region, the net flow, okay, of the chemical, the density, the change in the density, basically the net flux of you, okay, through this boundary of the V, yeah, that is going to be zero. Yeah, so if F denotes the flux density, then in that direction, in any direction, whatever the gamma is, yeah, in any direction gamma, the flux density, if you take the integral of that, that is going to be zero. Yeah. Now, if that is the case, from Green's theorem or Gauss theorem, actually, from from Gauss divergence, if you remember, when you looked at integration by parts, okay, I said that it is going to be one of the most important, how do I put it, most important thing you can learn, integration by parts. So okay, we are going to use that integration by parts. So here, so let's say that integral del v f dot gamma ds is zero, yeah, then you use Gauss divergence and say that, you see, integral over v, the divergence of f okay, d of x, that is equals to integral of del v f dot gamma ds, right? And that is going to be 0. Yes. How are you getting? This is Gauss divergence theorem. So basically, GD, Gauss divergence theorem. Okay, Gauss divergence theorem says this, and from here we get this flux is 0. Okay. Now, see, this V is arbitrary, right? This V can be anything. So you are saying that a object, when you integrate that object over any subregion, smooth subregion, that is going to be 0. What does that say? That the divergence of F is going to be 0 in V. Okay, V is arbitrary, of course. In omega, arbitrary. Okay, in omega, I have to say it is in omega. Why it is in omega? See, V is contained in omega, right? V is arbitrary. So you are saying that you are taking the divergence, you are taking some object and integrating it in any smooth subregion of omega, and that integration is 0. Yeah. So definitely the object in question, that is going to be 0, right? If you are not convinced here, please check this part. Okay. So check this. Check that let's say u is in c, let's say 2 of omega be such that integral over, let's say, u, okay, and dx over v, this is 0 for any smooth v containing omega. Okay, then u has to be 0 in omega. Okay, see, one thing is this: why am I talking about smooth v in omega? If you remember, Gauss divergence theorem says that you have to have this region where you are integrating, that region has to be a smooth region, right? At least C1. So that is why I'm just assuming it to be smooth. Okay, now you see, uh, there is something called, so since we are talking about chemical concentration, there is something called a Fick's law. Okay, Fick's law of diffusion. This is from your physics. Okay, Fick's law of diffusion, that says that the flux density F is proportional to gradient of u, right? So basically what it is saying is minus some constant times gradient of u. Okay, right? So why minus? Because the flow, the flux density, the flow, okay, is from the region of higher to lower concentration. See, if there is a flow in the system, here it is now, huh? If there is a flow in the system, that is always going to be from a region of higher concentration to the lower concentration, right? So that is why this negative sign is there. It's just say that the flow is somehow, in a negative way. And this C, of course, is a constant of proportionality. I mean, we are just saying that F is proportional to gradient of U. Okay, and gradient of U is just the change of, the flux. So basically, the change of the density. So, and this C is positive, we are assuming, because otherwise there's minus C, we'll get it. So, if F is minus C times gradient U, let's just put it here. Therefore, divergence of minus C times gradient of U, that will give you minus C times divergence of gradient of U, right? That will be 0, because divergence of F is 0. F looks like this, so divergence of gradient U is 0. So that will give us that Laplacian of U is 0, because C is positive, right? Since C is positive, that will give you, or minus Laplacian, I don't care. I mean, it's okay. Now, see, the very important thing is, this is from Fick's law, we got that Laplacian of U is equal to 0. Now, you just, if you want to, so this is an Laplace equation, okay? So that's a Laplace equation. The whole idea of this is, see, here, if it is a chemical concentration, you are talking about Fick's law. Okay, Fick's law will give us the Laplace equation. Actually, if it is a Fourier law of heat conduction, that is also similar to this. Yeah, if the Fourier law of heat conduction, then that also will give you a Laplace equation. Okay, in that case you will consider, so let's say for heat conduction u will be your temperature, the function u, and if it's a Ohm's law electricity conduction, then u will be the electrostatic potential. Okay, so this is a very important thing to understand. Okay, so with this, what we are going to do is, in the next set of lectures, we are going to talk about how to work with Laplace equation. Yeah, so with this we are going to end this particular video.